All right, guys, we're back with video number 4 for confidence intervals of a population mean. And in this one, I'm going to show you how to do actually the four-step process for a one sample t interval for a mean. And that's the name of the procedure that we would use when we want to calculate a confidence interval to estimate mu, the population mean. So one sample t interval for a mean is a confidence interval used to estimate population mean mu when the population standard deviation sigma is not known or unknown. So here we go with an example. Manufacturer of a high resolution video screens must control the tension of the mesh wires that lie behind the surface of the screen. Too much tension will tear the mesh, and too little will allow wrinkles. The tension is measured by an electrical device with output readings in millivolts. Some variation is inherent in the production process. The table gives the tension readings from a random sample of 20 screens from a single day's production. So we have our sample here, and we're asked to construct a 90% confidence interval for the mean tension mu of all screens produced on this day. So we're going to walk through the four-step process here for this one. So our first step is to state. Remember, to when we follow the four-step process, in the state step, you want to state your confidence level and define your parameters. So we want to construct a 90% confidence interval for mu equals the mean tension of all the video screens produced this day. Okay, it's very important that you have both of those things and you define the parameter in context of the problem. Make sure you give the detailed context as well. The next thing we want to do is the plan step. So we're going to check the conditions, but before we check the conditions, we have to state what we are checking the conditions for. So we're doing a one sample t interval for a mean, which again, we're going to check the random 10% and normal large count condition. So we have the random condition was a random sample of 20 video screens produced that day. Again, you can't just list random 10% normal large sample and put a check mark. You have to explain or show how each one is satisfied. 10%, it's reasonable to assume that 20 is less than 10% of all video screens produced that day. And for the normal large sample condition, since our sample size is less than 30, we have to create a data display, a graph of the data. A dot plot will do, but you not only have to add the dot plot and label it, and the easiest thing to do is to construct it on your calculator and then just copy it onto the paper. But you have to make a comment. The dot plot does not show strong skewness or outliers. Very important. You need a dot plot, you need it correctly labeled, and you need to explain how it satisfies the normal large sample condition, which basically can't show any strong skewness or outliers. Okay, so the next step we're going to do is the do step where we actually make our calculations. Now, for the do step, you can use your calculator to find the mean and standard deviation of the sample data. You can enter it right in and get those summary statistics there. So in the do step, what you do want to list is X bar, which is 306.32 millivolts, the standard deviation of X, which is 36.21 millivolts, and the sample size, which is 20. So with 90% confidence, the degrees of freedom is 20 minus 1, which is 19. Important to put the degrees of freedom there. So we could use the T star or the table B, and we get a T star value of 1.729. Okay. Now, to construct our confidence interval, you have 306.32 plus or minus 1.729 times 36.21 over square root 20. Remember, the standard error is the standard deviation of the sample divided by the square root of the sample size. So this is going to be 306.32 plus or minus 14.00, and giving us a confidence interval of two 292.32, comma 320.32, with degrees of freedom of 19. Okay, so using technology, you can construct the confidence interval as I showed you in the previous video. So the final and last step we want to do is actually write our conclusion to be able to interpret what this confidence interval is. And so our interpretation, our conclusion rather, is that we are 90% confident that the interval from 292.32 millivolts to 320.32 millivolts captures the mean tension of all the screens produced on this day. So it's very important that you use the confidence level, the confidence interval, and this specific information in the problem, the specific context to answer the question. So we have a second part to this one based on the interval just found. Is there convincing evidence that the screens produced this day don't meet the manufacturer's goal? And we have to explain our reasoning. So just putting a yes or no is not going to be sufficient here. Well, because 300 millivolts is within the interval of plausible values for the population mean, based on this confidence interval, we don't have convincing evidence. So we just need to state that in a concise but thorough manner, in a statement here. So we would say no, because 300 millivolts is within the interval of plausible values for mu given by the confidence interval 292.32 to 320.32. There is not convincing evidence that the video screens produced this day don't meet the manufacturer's goal. Okay, so we have our yes or no answer. We have our uh, interval in there in the context and whether or not it's convincing evidence. Okie dokie. So one of the tips to keep in mind is that while you can use your calculator to compute a confidence interval on the AP Stats exam, there is a risk. If you just give the calculator answer with no work, you'll either get full credit for the do step or no credit. So full credit if it's exactly right, or no credit if it's exactly wrong. If you opt for the calculator only method, make sure you complete the other three steps and give the interval in the do step. Okay, so no matter what, you have to do the four-step process, even though you can calculate the whole interval on your calculator. You need to follow that whole four-step process. And then just a quick nugget about the margin of error. So previously, we learned how different factors affect the margin of error when you calculate a confidence interval for a population proportion. And in this context, much the same thing. The margin of error, T star times standard deviation of the sample over the square root of the sample size, in a confidence interval for a population mean decreases as sample size increases, assuming the confidence level and sampled standard deviation remain the same. The margin of error is proportional to 1 over the square root of the sample. So essentially, if you quadruple the sample size, you're going to cut the margin of error in half, assuming everything else remains the same. Also, the margin of error will be larger for higher confidence levels. So that makes sense because wider intervals will have a greater capture rate than narrower intervals. And then finally, the margin of error doesn't account for bias in the data collection process. It only accounts for sampling variability. All right, so that's it for this one, guys. Hope that was helpful to you. Take care.